So far what we have talked about is about how you can represent any kind of input signal, any kind of signal, using superpositions of what we call basis signals, right? In lesson 2, we basically talked about this kind of representation, basically representing any kind of signal as a superposition of weighted or scaled and shifted delta pulses or impulses, right? That was basically the content of lesson 2, and we talked about this kind of representation and the consequence of this kind of representation in terms of the convolution operations and that kind of thing, other properties, right? And in lesson 3, so far what we have talked about is how to use complex exponentials, this kind of function, as what we call basis signals, right? How we can actually represent an arbitrary signal as superpositions of this kind of basis signals. We're basically talking about some of the properties of complex exponentials as basis as basis signals, right? The reason that we would like to use this kind of complex exponentials as the kind of building block for any kind of a complex signal is that this kind of complex exponential is actually the eigenfunction of a linear time-invariant system. So if you actually use this basis signal as an input to a linear time-invariant system, what's going to be the output, right? So the output, you can compute the output by computing the convolution of the impulse response with the input signal, right? Which is the complex exponential, one of our basis signals, right? And then we can do some mathematical manipulations, and we end up with this kind of expression. So the first thing that I have noticed is that you have the input signal that's repeating here, right? So this is the input signal, and then the output signal also contains the input signal, and it's basically the input signal multiplied with a number, a scalar. And this scalar, what I was telling you is that this scalar happens to be the Fourier transform of the impulse response at the frequency of the complex exponential that you used as the input, right? So now you see the kind of benefit of using this kind of a signal as the basis signal, right? Because if you put this basis signal into a linear time-invariant system, you get a scaled version of the input signal back, right? So the operation is really simple. So if you can actually represent xn, any kind of a signal, as a linear superposition of complex exponentials with different frequency, omega k is the index, omega k is the parameter, right? And then if you put this particular input into a linear time-invariant system, you can compute the output very easily. The output is just going to be the output for each of the basis signal, which is a complex exponential, right? And that's the thing here, right? You put this thing into the linear time-invariant system, because it's an eigenfunction, you get the same thing back, right? And then with one more scalar multiplied on it, and this scalar happens to be the Fourier transform of the impulse response at omega k, which is the frequency of your basis signal, right? And then all you have to do is to multiply ak, that's the coefficient, and then do a summation over k, right? And that was sort of the basic theme, or the most important idea of our representation, right? And then I told you how to actually compute this coefficient. What I was telling you is that you have to do a Fourier transform in order to compute the coefficient, right? And I was showing you sort of a specific Matlab implementation, so Matlab algorithms for computing the Fourier transform, right? When we did the Matlab implementation, we have to have a sample of the frequency axis, and the sample that we used is here. Omega k equals to pi divided by big M times k, and small k goes from 0 to big M, integer, right? It's all integers, right? So omega basically ranges from minus pi 0 to pi, basically, right? That was how we actually computing the Fourier transform. I gave you the formula for computing the Fourier transform for any kind of omega, right? But I did not tell you how we got this kind of formula, right? We were not very specific about how we actually got this formula. But one of the things that you have to pay attention to is that this formula doesn't actually specify a sampling of frequency omega, right? It doesn't really specify how we should sample the omega. Here, omega is treated, the frequency is treated as a continuous variable, right? So when we did the Matlab implementation, we were specific about how to sample omega, right? We gave omega k this kind of a linear distribution. It's a kind of an evenly spaced sampling of 0 to pi, basically this interval, right? And another thing that we were not sort of so specific about is when we did this kind of representation, right? We were not very specific about what exactly is omega k. We did not sort of say exactly what omega k would be, right? For this kind of representation. So now let's try to be more specific, and let's try to be more specific, right? And let's talk about what we call the discrete Fourier series. And let's talk about what we call the discrete Fourier series, or DFS, right? In which we're going to make specific about what omega k is going to be, right? So now we know what's actually the benefit of using these kind of complex exponentials as the basis signal, right? Because it's an eigenfunction of a linear time-invariant system. An eigenfunction is what? An eigenfunction is some kind of special function. If you put this function as input into a linear time-invariant system, the output is just going to be the same as the input signal multiply just the scaled input signal, right? Multiply with a scalar, and that scalar happens to be the Fourier transform of the impulse response at the frequency omega k, which is the frequency of your input signal, right? Input basis signal, right? So how do we want to sample omega k, right? When we did the inverse Fourier transform, omega k was basically just an even sample from 0 to pi, right? Let's still do the same thing. Let's still try to do the same thing. We're gonna still take an even sample, right? So omega k equals to k times 2 pi divided by big N. Big N is a constant. Suppose 100, 1000, doesn't really matter. You can determine you can specify what big N actually is, right? But it's just a very large constant. You can think of it as just a very large constant. You can just think of it as 100, for example, right? And then k, small k, goes from 0, positive minus 1, positive minus 2. So small k is just all integers. Again, an even sample. Omega k is an even sample of the real axis with the interval, with a sampling interval given by what? Given by 2 pi divided by big N. So if your big N is very large, then omega k is going to be a very dense sample of the real axis. If big N is small, 10 for example, then it's going to be a very sparse sample of the real axis, right? So you can imagine what omega k would be, right? And if we specify omega k like that, then we can look at e to the j omega kn, right? This basis signal. We can bring the expression for omega k back into e to the j omega kn, and let's call it phi kn. Let's just call this complex exponential phi kn. Right? We'll give it a name because it's going to be easier to manipulate later on, right? And then if we bring the expression for omega k back into e to the j omega kn, what we have is e to the jk, right? E to the jk times 2 pi divided by big N, and then times n, right? That's going to be our basis signal. And there are several things that we have to sort of notice about this phi kn, this kind of special function, right? This kind of function. It's a complex exponential, right? It's absolutely a complex exponential, right? But if we actually look at how phi k actually changes with the index k, the subscript k, we can find some very interesting properties. So if k equal to 0, for example, phi 0, right? Phi 0 n equals to what? E to the j times 0 times everything. So it's a so it's basically 1, right? E to the 0th power, it's 1, right? That's phi 0 n. And phi 0 n happens to be equal to phi big N n. So if k actually equals to big N, so if k actually equals to big N, you bring big N into it, right? Big N cancels out, becomes j 2 pi times another integer n, right? So it's e to the jth power, e to the j times 2 pi times integer, this, and it also equals to 1, right? If you think about it in the complex plane, this number under selection is basically the phase angle, right? So 2 pi is the phase angle, right? 2 pi times n is basically phase angle, and n is an integer. So it basically means that it lies on the real axis because the phase angle is 2 pi times an integer, right? So phi 0 equals to phi big N, right? Right. And if we look at the phi 1n, so k equals to 1, right? K equals to 1. Then it becomes e to the j 1 multiplied 2 pi divided by big N times n, right? And then what exactly is phi big N plus 1? So if you bring k equals to big N plus 1 into this expression, right, what you will find is that big N is going to cancel out, right? And you have a term that's e to the jk times 2 pi, e to the j times 2 pi times n. That's one of the terms, right? Again, it's a complex number with a phase angle equals to 2 pi times the integer, so it's 1, right? And then you multiply with what? Don't forget k equals to big N plus 1, right? So 1 multiplied 2 pi divided by big N times n happens to be exactly equal to phi 1n. You can check phi 0, phi 1, phi 2, right? So phi 2n equals to phi big N plus 2n, right? So basically this kind of phi k sequence has some kind of periodicity with respect to k, right? Do you see? And this periodicity with respect to k can be summarized in this particular formula. So phi k n equals to phi k plus r is an arbitrary integer times big N. So if r equals to 1, then what you have is phi 0 equals to phi big N n. Phi 1 equals to phi big N plus 1, right? Phi 2 equals to phi big N plus 2. It's exactly the formula that I gave here, right? So if you are actually doing a summation over all the phi kn, you don't really need to sum over all possible values of k in this case, right? Because phi is periodic with respect to k. Phi 0 equals to phi big N. Phi 1 equals to phi big N plus 1. You don't really need to sum over all possible values of k. All you have to do is to sum over a set of unique values of phi k, right? Unique values. So k can start from 0, n with big N subtract 1. Or it can start with value of 1 and n with big N. Or it can start with value of 2 and n with big N plus 1. That kind of thing. As long as you can select a continuous segment of this integer axis that has big N values in it, right? It can start from any value, end with that value plus n, subtract 1, right? And then you have sampled through all the possible values of phi k, right? So k can start from 0, end with big N subtract 1, right? That's one possibility. Or k can start from 1 and end with big N, right? That's another possibility. It doesn't really matter where the starting value or ending value is, right? As long as it has a sequence of big N non-repeating unique integers, continuous integers in it, then this you have sampled through all the possible values of phi k, possible unique values of phi k, right? So that's xn. That's xn. If we actually pick a specific value of omega k, then we can actually recover xn. We can sort of represent xn using this kind of summation over weighted summations of phi k, right? Weighted summations of all the unique phi k's, right? Now let's look at how we can actually determine ak, right? I gave you a formula, but once we have picked a omega k for this kind of representation, how we actually specify ak, the coefficient, how we can compute ak, right? The coefficients. Now let's before we actually talk about how we figure out what's actually the coefficient ak for this particular choice of omega k here, right? Let's look at some important results. One of the results is called a geometric series. This summation is called the geometric series, right? So it's basically a summation of the power of arva, and the power is n, and n goes from 0 to big N subtract 1, right? It's called a geometric series. You guys probably have heard about it when you are in high school math, right? If you don't exactly remember what the geometric series actually is, you can Google about it, and there's a Wikipedia pages explaining how you actually what geometric series actually is and how you actually can derive these kind of results, right? But here we are not going to sort of prove how we actually got this result, right? But when arva equals to 1, that's arva here, then it becomes 1 to the nth power. 1 to the nth power is still 1. You end up summing 1 for like a big N times, right? And the result is big N, right? And when arva is not equal to 1, you have this kind of formula, right? It's basically 1 subtract arva to the big Nth power. That's big N is basically the term of your summation, right? How many terms you are involved in the summation, and then divided by 1 subtract arva. That's what we call the geometric series, right? And I would encourage you to Google about the geometric series if you don't remember this particular result, right? Now let's look at this kind of summation. What I claim is that this summation is actually a geometric series. So the summation index n goes from 0 to big N subtract 1, right? It's exactly the same here. And then the arva, what exactly is arva in this particular formula? The arva is e to the jk times 2 pi divided by big N. That's arva, right? So if you consider e to the jk 2 pi divided by big N as arva, then arva's nth power, arva to the nth power, becomes e to the jk 2 pi divided by big N times n, right? So your arva is, in this particular formula, is e to the jk 2 pi divided by big N. So now we can actually use the result from the geometric series, right? When arva equals to 1, that's e to the jk 2 pi divided by big N equals to 1, right? So when does e to the jk 2 pi divided by big N equals to 1, right? When k equals to 0, plus minus big N plus minus 2n, right? That kind of thing. Then e to the jk 2 pi divided by big N equals to 1, right? If that's the case, then the summation result is big N, right? And when k is not equal to this kind of values, then arva is not equal to this term is e to the jk 2 pi divided by big N is not equal to 1, right? In that case, you have to use this particular equation. It's basically 1 subtract arva, that's our arva here, right? And then 1 subtract arva to the big N's power, alpha to the big N's power. So big N cancels out. Jk 2 pi, right? That's e to the jk 2 pi. And you know that k is an integer. E to the jk 2 pi with k equals to the integer exactly equals to 1. So the numerator is 1 subtracted 1. That's exactly 0. So the summation, this particular summation here, equals to either 0 or big N. And when do we get big N? When k equals to 0 or positive minus big N, positive minus 2n, that kind of thing. If it is an integer times big N, right? Then you get a big N. The summation result is big N. Otherwise, the summation result is 0, right? And now we can actually try to figure out what's actually big AK here. We can try to figure out what's actually AK here, right? So the way that we are doing it is, so this is our formula. This is our formula xn, our representation of the input signal as a linear superposition of these kind of complex exponentials with omega k that's kind of determined by this particular sampling sequence, right? K times 2 pi divided by big N. Now what we have to do is to multiply both sides of the equation with another complex exponential, that's e to the minus jr 2 pi divided by big N times n. And r is another integer. It could be a different integer from k, right? But it's another integer. It's just a integer, right? We multiply both sides by this particular complex exponential, and then do a summation over n. We do a summation over n on both sides, right? So now on the right hand side, on the right hand side, we have both a summation over n and also a summation over k. The coefficient ak depends upon k, right? And then the complex exponential here, we can sort of rearrange terms. Then it becomes k subtract r times 2 pi divided by big N times n, right? So since ak doesn't depend upon n, we can take it out of the summation from n, for n, right? So we can switch the order of the summation here. So ak summation over k, that's everything that's related to k here, and then the only term that's actually related to n is this complex exponential here, right? That's the summation over n e to the j times k subtract r 2 pi divided by big N times n, right? And then we need to evaluate this particular summation here, what this summation actually equals to. And now we can use the result from the previous slide here. We can use this result, right? But instead of j times k times 2 pi divided by big N times n, the complex exponential now has a value that's k subtract r times 2 pi divided by big N times n, right? It's not k anymore, but it's k subtract r. The summation over n is exactly the same as here, right? The summation over n, that's exactly here. E to the j is exactly the same. 2 pi divided by big N times n is exactly the same here, right? Except that k has been replaced by k subtract r, right? And the result here is that most of the time, this summation actually equals to 0, unless k equals to integer times big N. And the summation result here is going to be k subtract r has to equal to big N times the integer in order for the summation to be non-zero. Otherwise, it's all equal to 0, right? So let's just because the index k is not sort of arbitrary, because when we talked about this particular summation, we have fixed k to be a consecutive interval of integers, right? That has a big N, this many number of integers in the interval. It could start from any value, but the total number of integers in that interval is big N, right? we have fixed k to a consecutive interval of integers, and the number of integers is big N. So when we write down this formula, we actually fixed k to that particular range, right? So what's going to be the summation here, right? What's going to be the value of the summation here, right? So when r equals to k, when r equals to k, then you get a value of big N. When r not equal to k, you get a value of 0 for this particular summation, right? And there's a summation over k here. There's a summation over k here. So you can imagine, so when r equals to k, then what you have is a k times big N, right? And when r is not equal to k, when k is not equal to r, basically, when k is not equal to r, then this whole term becomes 0. So this summation over k eventually leaves only one term that's non-zero. That's ar, right? That's ar. So when k actually equals to r, this summation actually equals to big N, right? And when k is not equal to r, this summation is 0. So all the non-r terms contribute 0 to the summation. Only one term actually contributes to this particular summation over k. That's ar. So you have ar, right? So ar times big N equals to this side of the equation. That's this term. So ar equals to 1 divided by big N, xn e to the jr, because k equals to r, right? K equals to r. So r equals to k also. So you can replace r with k, right? So eventually what you actually have obtained is ak equals to sort of, you can replace r with k, right? Doesn't really matter which index you actually use. So if we actually summarize the representation of the sequence as superpositions of weighted complex exponentials, right, with a fixed interval, with a fixed sampling of omega, then your coefficient ak can be obtained by using this formula, the formula here we obtain here. And this is a discrete Fourier series transformation pair, basically. This is called a synthesis. This equation is called a synthesis equation. And this equation is called the analysis equation. You get the coefficient ak by doing what we call a DFS transform, or discrete Fourier series calculation. You're computing the series coefficient, right? That's the coefficient. You can get the coefficient by doing this kind of formula, by using this kind of formula. Once you have the coefficient, you can resynthesize the original signal by doing this superposition. You see? So this is called a DFS pair. And let's take a look at the one properties of AK. We have looked at the phi k, all the complex exponentials, right? We have this kind of important property here. So phi k equals to phi k plus r times big N. We have this very important property here. So it has so phi, the function phi is not really sort of unique. It repeats itself according to k. Right. Now let's look at the AK. Let's look at the coefficient AK. Right. Let's look at the coefficient AK. The coefficient AK is basically the term, the constant, the number that's multiplied in front of the phi k. Right. So this is phi k basically. Right. So what I was telling you is that this summation over k is not exactly unique, right? K can start from any integer as long as it's a big N, this number of consecutive integers. The summation is fine, right? You can recover the input sequence without any kind of problem, right? So let's try to sort of put that into practice. So xn equals to, if we start k from 0, if we start the summation with the k index starting from 0, then you get a0 phi 0 plus a1 phi 1 plus until a big N subtract 1 phi big N subtract 1. Right. But you can also express xn using a different starting number. So k start for here k starts from 1. So because a1 phi 1 plus a2 phi 2 plus a big N phi big N. Right. And then you can just subtract these two equations. Subtract these two. The left hand side xn subtract xn, that's 0, right? And then the right hand side it's a1 phi 1 subtract a1 phi 1, a2 phi 2 subtract a2 phi 2, that kind of thing. And then up to a n subtract 1 phi n subtract 1 here, right? And then you also have another term here, that's a n subtract 1 phi n subtract 1, right? So eventually you end up with a0 phi 0 subtract a big N phi big N. That's on the right hand side, right? The left hand side is 0. And don't forget we have the result phi 0 equals to phi big N, right? Phi 0 equals to phi big N. So the right hand side is basically a0 subtract a big N, and then times phi 0 basically, and that equals to 0. So you can get out of that from that equation that a0 equals to a big N. And you can repeat the same kind of analysis, and eventually you're going to get a1 equals to a big N plus 1, a2 equals to big A n plus 2, that kind of thing. So the coefficients are also periodic with respect to k, you see, right? So a0 actually equals to a big N, just like phi 0 equals to phi big N. a1 equals to a n plus 1, just like phi 1 equals to phi n plus 1. Right. So this coefficient, this DFS coefficients, or the spectral coefficients, right? Spectral coefficients is also periodic with respect to k. And now let's write some code. Let's write some Matlab code to implement this DFS pair, right? And the idea is actually quite simple. It's pretty much the same. It's pretty much the same as what we were doing before, right? I on one of the slides I actually have listed the Matlab algorithm, right? The Matlab implementation, how we can actually implement. At that time, we were not specific about the frequency sampling, right? But now we are specific about it. But the idea is pretty much the same. The algorithm is implemented using a similar idea. So now let's look at the analysis equation. That's the DFS equation. So let's look at how we can actually compute the coefficients ak, right? And here's the function. Here's the Matlab function, and the function name is just called DFS, right? DFS, and it takes two inputs, xn. That's the amplitude of the input sequence, right? That's the amplitude of the input sequence, and then big N. Big N is basically this big N here. That's this big N, right? And then we are just basically implementing this particular summation as a matrix vector multiplication here. So I'm going to construct this particular matrix. That's this complex exponential e to the minus jk 2 pi divided big N times n. Right? You have two indices. One is n, the other is k. Right? So and then this is a vector, right? Xn is a vector, right? It has just one index n, and then it's a summation over n, summation over all the n index, right? And then let's try to construct the two axes first. So n goes from 0 to big N subtract 1, right? And then k goes from has exactly the same range, right? And then big Wn Wn is basically this complex exponential. It's e to the minus j omega, jk times e to the minus j times 2 pi divided by n, right? That's this complex number exp minus 1i minus j here. It's the same thing. 2 pi divided by big N, right? And then I'm gonna construct n times k, these two indices, right? These two indices are gonna be constructed using a cross product or matrix vector multiplication, matrix multiplication. So n for now it's a row vector. Transposing it, give it a column vector. A column vector with big N, this many elements in it. And then k, small k, is a row vector with also big N elements in it. So it's a column vector times a row vector. And you end up with nk. Nk is a matrix that's big N times big N. This many big N rows and big N columns, right? And then if I want to construct this complex exponential as a matrix, all I have to do is to take the dot hat, that's a component-wise power, right? And the Wn is the constant, right? The complex constant. So once we have this Wn nk, this complex exponential as a matrix, all we have to do is to do a matrix vector multiplication with xn, and then the result big xk is basically ak, this coefficient. Right. And that's the analysis equation. Don't forget about divided big N. You have to divide big N here, divided by big N here, right? That's the analysis equation, right? Now let's look at the synthesis equation. We can still use the same idea. We can still implement the synthesis equation also as a matrix vector multiplication. Right. That's the synthesis equation. Function for computing the inverse. That's the synthesis. And the function name is called IDFS. Right, inverse DFS basically. And it takes two inputs. xk, that's the coefficient ak, and then big N, that's the big N here. Big N, right? And then we are still gonna have to construct the two axes N and K, right? But now the number here is different. The constant number is e to the jk, e to the j times 2 pi divided by big N. So let's just use 1i, right? 1i, j is 1i, times 2 pi divided by big N. Right? That's gonna be our complex constant. We're gonna construct n and k times n, this matrix in the same way, right? And then this complex exponential as a matrix can then be constructed by using a dot hat. Right, component-wise taking the power, and eventually this xn, this synthesis equation, can be reconstructed by doing that, by doing a matrix vector multiplication. That's the synthesis equation, right? So now let's do an arbitrary example and test these two functions, right? So if we actually do an analysis of an input signal, get the coefficients, right? We can get the DFS coefficients AK, big AK. And then after we get the AK, we can use the synthesis equation, right? And then try to recompute the input sequence xn, right? And then we can compare this synthesized xn with the original xn and see if they are identical to each other. So basically that's the example that we're gonna try. So let me construct x. I'm just gonna use like a 1 row 10 column, this kind of random number, right? If we wanna take a look at the sequence, we can do a stem x, right? That's our input sequence, some random numbers, 10 random numbers basically. And then let's compute the coefficients. Big X equals to DFS. Let's just use our DFS function, this function, right? X as the input, and then 10. That's the total number of non-zero elements in small x, right? and that's going to be our coefficients. Right. Before we look at the coefficients, let's just do an inverse transform. Let's just do a IDFS of the coefficients and see if we can actually recover the input signal. Let's just call x1 equals to IDFS big X, again 10, right? And then let's just compare x1 with x. Let's hold on to the old plot, and then let's just do a stem real x1. The reason that I need to take the real part is because there are numerical errors. There are numerical errors. Those numerical errors are going to introduce very small imaginary parts, right? And those very small imaginary parts are going to screw up the plots. So I need to take the real of x1, right? And then let's plot it in red and see if they are identical to each other. Yes, indeed, they are exactly the same. They are exactly the same, right? And we can sort of take a look at the coefficients now, right? So that's big X, right? That's the Fourier series coefficients. So let's look at its real part. Let's just do a stem. The real part of big X, right? That's the real part. And then let's look at the imaginary part. And that's the imaginary part. Right. And you can sort of see the imaginary part seems to be antisymmetric, right? Seems to be antisymmetric. And then the real part seems to be symmetric, right? Except for this stick at the beginning, right? Otherwise, it's sort of symmetric. The same is true for the imaginary part, except for this first point. Otherwise, it looks like it's antisymmetric, right? We're gonna look at the why later on, well, after we have talked more about DFS, right? Now let's look at a slightly more complicated example. So xn, that's our signal. Now it's composed of sines and cosines, right? Sines and cosines. It's not just a random sequence. It's 1 plus sine 2 pi divided by big N times n, plus 3 cosine 2 pi divided by big N times n, plus cosine 4 pi divided by big N times n plus pi over 2, right? So it's a composition of sines and cosines. Right. Let's try to make a plot of this particular function, right? So x equals to 1 plus sine 2 pi divided by big N times n. Let me specify. Let me show you what big N actually is. Big N equals to 100, right? Let's just use 100. It seems to be a good number. It doesn't really matter. You can just change big N to some other number. It doesn't really matter. So small n, that's small n here, goes from 0 to big N subtract 1. So that's exactly 100, right? And then all we have to do is to sort of compute x as a summation. So it's 1 plus sine 2 pi divided by big N times n. That's the first term, right? That's the first and the second term. Plus 3 times cosine this thing. Plus cosine 4 pi divided by big N times n plus pi over 2. Right. So that's our x. Let's make a plot of it. Let's make a plot of it. Nx, right? So that's our function. So if you want to look at the individual components, you can also do that, right? So all you have to do is to sort of. So that's the first component, right? And then if you want to look at the second component, no, the third component actually. That's the third component. Here I'm using plot, I'm not using stem. So if you want to use stem, it's also similar. Right. So you sort of see the three components. All of them are actually harmonics, right? All of them are actually harmonics. And for this particular sequence, we can actually manually compute the Fourier series by hand, just by hand. So in order to do that, we need to use the Euler's equation, and then we can write sine and cosine, these sine and cosine functions, as superpositions of Euler's equations. right? So that's sine, right? Sine. So we can write sine as one exponential subtracted the other exponential, right? So it's an exponential. Then the coefficient here is 2 pi divided by big N times N, right? And then if you write this as two exponentials subtracting each other, then that's like that, right? So it's e to the j 2 pi divided by big N times N subtract e to the minus j 2 pi divided by big N times N, right? And then if you subtract these two, the result is 2j. It's actually 2j sine 2 pi divided by big N times N. So you need to sort of divide 2j here. And then you can do the same thing for cosine, for the cosine. So it's so e to the j 2 pi divided by big N times N. Right, it's cosine plus I sine 2 pi divided by big N times N. Subtract cosine 2 pi divided by big N times N. Subtract j sine 2 pi divided by big N times N. Right. Don't forget that you have a coefficient of 3 here, right? And then the two cosine, the sine terms is gonna cancel out, but the cosine terms is gonna sort of. And then this term actually gives you this cosine, basically. Don't forget the 3 here. And then you have to divide by 2, because cosine plus cosine, that's 2 cosine, right? And then you have to divide by 2. And then you deal with this last cosine in the same way. Last cosine in the same way. And then you can reorganize all the exponentials in a specific order. So here I'm actually reordering it, right? So here the first term is actually corresponding to k equal to 0, right? K equal to 0. The second term actually equals to corresponding to k equals to 1. This is k equals to minus 1. You see, there's a minus 1 here, and then that's 2, and then minus 2. So you can sort of read the coefficients directly from the formula. So a0, the zeros term, equals to 1, and then a1. So that's the a1, right? But you have to pay attention to the j. J is on the denominator. So if you want to move j to the numerator, you have to sort of multiply j on both the denominator and numerator. And then j times j is minus 1. So it's a 2/3. No, 3 over 2 subtract half of j. Right? And then that's a minus 1. That's a minus 1. And then a2. Right? And then that's a minus 2. So you got like all the coefficients just by sort of doing this kind of analytical analysis, right? And every other k, the coefficients for every other k actually equals to 0, so you don't really have to worry about any other things. So in this particular equation, I was showing you a0 equals to a big N, right? a1 equals to a big N plus 1. Big N here is equal to 100 here. So basically a0 equals to a100. a1 equals to a100 plus 1. a101, right? So a minus 1 equals to what? A minus 1 equals to a big N plus minus 1. That's a big N subtract 1, right? That's big N subtract 1. So it's a 100, and big N equals to 100. So big N subtract 1 is 99, right? So this is actually a 99, right? That's a 99. And then a minus 2 is what? So it's a minus 2 equals to a minus 2 plus big N. Big N is 100. So a minus 2 equals to a 98, right? So now let's do our numerical analysis. Let's just use our DFS function. Let's use our DFS function to compute the coefficients and see if that actually equals to our analytical results, right? So let's just call DFS. So x equals to DFS x big N, right? That's our big X. So now let's compare our coefficients. Because Matlab actually has an index that starts from 1 instead of 0. So if we want to look at a0, we have to look at big X1 here. That's exactly 1, right? And then let's look at the a1. a1 corresponding to big X2. Right? That's a 1.5 subtract 0.5j. That's 1.5 subtract 0.5j. Numerical error. It's unavoidable, so it's not exactly 1.5, right? But it's 1.4999. It's very close to 1.5, right? And then here it's minus 0.5, right? And then let's look at x3. x3 corresponding to a2 here, right? x3 corresponding, it should be 0.5j. So it's a 0.5i here, right? And then there's a very small real part, but it's close to 0. Right? That's x3, that's a2. Right? And then let's look at a minus 1. A minus 1 actually is the same as a99, right? And a99 here actually equals to big X100, right? Don't forget to add 1 next to it. It's a 1.5 plus half a j. It's a 1.5, almost 1.5, right? Plus 0.5j, right? And then let's look at a minus 2. A minus 2, that's 98. That's 98, right? 98, in our case, it's a 99. It's almost 0, right? Almost 0. And minus 0.5 I, minus 0.5 j, right? So it shows that our code is actually correct. It's actually returning the correct sequence, right?